And we cannot let it change because all these other dominoes will fall and it'll be chaotic. Hey folks, welcome to the channel. I'm Don. I'm a reaction today to Dr. Becky Smethurst's Problem with Background Microwave Radiation. This title caught my eyes. I've seen some of her videos. I haven't seen this one, but I've seen some videos over the past few years. She was like all excited as I was about James Webb Space Telescope and all that. I've got my UK hat on right here because that's where she teaches at University of Oxford. But it caught my attention because I read this book, Losing the Nobel Prize, and by Brian Keating. And I think he almost won the Nobel Prize. But it was about B-mode polarity and the cosmic is trying to get through the radiation. But one of the things that happens is the space dust is when you're traveling, studying things in vast distances, just a little bit of dust that's out there accumulates and it can mimic radiation and such. But I read this book and I learned a lot about it, financing, the missions, how I got financing, but the nature of the Nobel Academy and this. But I mean, you learn a lot about the subculture that goes on, but about his own research into it. And I think I did a reaction to something, or he was doing an interview with someone, but she's very bright and she's very likable. So I like exposing you guys to these various folks so you can make your own minds up on this stuff. Because I'm a philosopher by training. I'll consider things that are theological, non-theological, any part of it. I like neuroscience is arguably my favorite topic, but cosmology is equal. The problem with background microwave radiation reveal the age of the universe.
When we look out into the universe, there's a big problem. It looks the same in all directions and matter is roughly distributed. That is weird, right? Because if you think about it, nothing can travel faster than the speed of light, right? That's what Einstein's theory of special relativity tells us. So if you look in one direction in the universe and we see like the most distant thing there is, right? Where light has been traveling the entire lifetime of the universe before it gets to us here so that we can see it. And we do the exact same thing in the opposite direction for the most distant thing we can see, where light has been traveling the entire lifetime of the universe before it finally gets to us here so we can see it. Those two things shouldn't really look the same because they've never been in contact with each other before. There's no way that light has had enough time to travel from that part of the universe to that part of the universe over there. And yet they look the same and they have roughly the same properties. This is even more obvious if you look at the oldest light in the universe, what's known as the cosmic microwave background. You might have seen this picture of all these red and blue splotches representing the different temperature across the universe when this light was emitted. But did you know that from the coldest spot shown by the blue to the hottest spot shown by the red, that temperature difference is only 0.00001 Kelvin. It is absolutely tiny. What it means is that on average, when this light was emitted, the universe was roughly the same temperature everywhere. Like what heat there was had been evenly distributed to what's known as thermal equilibrium. Despite the fact that at that time, the universe was still too big for light to have traveled from one side to the other to communicate that information of what temperature.
I wonder what she means by communication. That's an interesting concept because when we think about it, we think about talking. It could be on our cell phones. It could be hand signals. It could be CB radios, ham radios. We think of communication that way. So what sort of information is she referring to and what sort of receptors and how would that communication impact the other?
Temperature it is over here versus over here. That information was over the light travel horizon. This is the horizon problem, and it's led to some really interesting ideas about the universe to try and solve it. So in this video, we're going to chat first what the cosmic microwave background actually is. Like, where does this light come from? 2, what we mean by the cosmic horizon and what the horizon problem is. And then 3, some solutions to the horizon problem, including inflation, a cyclical universe, and the idea of varying the speed of light. But before we do that, I just want to chat about our mental health, because I don't know about anybody else, but mine got a lot worse during the pandemic. Like, I developed anxiety for the first time, and I just put off dealing with it for far too long. Like, I'd make excuses, like I was too busy at work, or it just wasn't convenient to go to therapy. But then I discovered BetterHelp. This is a paid partnership with them. BetterHelp makes connecting with a therapist so easy and convenient for those of us who've struggled in the past to find time for therapy. The platform is online and your therapy is done remotely, whether that's by video call or by text, whatever you prefer, and so you can fit it in around your lifestyle. By filling out a few questions, BetterHelp can connect you with a credentialed therapist in under 48 hours in most cases. But if you don't fit well with that therapist, which is pretty common in therapy, you can just switch to a new one free of charge, which is so convenient. Look, I know that my anxiety is not a major mental health problem compared to what other people are going through, but therapy really did give me the tools to help manage it. So if any of this is sounding familiar, no matter how small you think your problem might be, give therapy a go. Try out BetterHelp and see if it helps you. Look, there's a link in the video description to betterhelp.com/Dr. Becky, which if you click, not only supports this channel, but also gets you 10% off your first month's therapy with BetterHelp. So thanks again to BetterHelp. And now let's get back to chatting about the horizon problem. And first, let's chat about what the cosmic microwave background actually is.
Okay.
Well, when I describe it in passing on this channel, I always say, it's the oldest light in the universe, which is true, but where does that light come from? We have to think about what the early universe was like, sort of in the first few 100,000 years of the universe is.
How does losing energy result in them binding together? I mean, I can visualize it, but I don't know if the properties really exist according to how I'm visualizing it.
Lifetime. It was much denser and therefore much hotter back then. So hot that all of your matter and your photons, your particles of light, was trapped in essentially one big blob of plasma that's opaque. Plasma is the fourth state of matter, where you've got electrons and protons separated rather than bound together in atoms. But then as the universe expanded more, it cooled down. Those particles lost energy, and slowly but surely they could then be bound together in atoms. Electrons bound with protons. Then you have gas rather than plasma, which is transparent, and those photons were free to stream wherever they wanted to. The universe was transparent for the first time. That happened when the universe was about 3,000 Kelvin in temperature and about 380,000 years old. That happened everywhere in the universe all at the same time, and that light was sent off in all directions. Now, because it takes light time to travel to us, traveling at the fastest speed there is, there's only so far that we can see out into the universe. This distance that we can see is known as our horizon, or the observable universe. Horizon because it inherits its name from the horizon here on Earth, right? That you can't see beyond. It's akin to that. You can actually calculate what our current horizon is in the universe fairly simply, right? Because distance equals speed.
The size of the universe, though, is different than the age of the universe. I think the size, she just said 13.8 billion, but I think it's theorized to be 90 billion light years across. We'll see if she touches on that in any way.
Times time. So if light travels at around 300 million meters per second and the universe has been around for about 13.8 billion years, then our horizon is how far light can travel in that time. It's currently around 130 trillion meters away, or 81 billion trillion miles, or 13.8 billion light years. Beyond that, we can't see anything yet because light hasn't had time to get to us. But as time passes, that horizon grows and new parts of the universe enter into what we can observe, and the first thing that we detect from those parts of the universe is the light that's been traveling for the longest, the oldest light in the universe, the cosmic microwave background. So what's the horizon problem then? Well, if we think about it, how big the horizon is in the universe depends on how old the universe is. So when the universe was much younger, the horizon was much smaller. We can actually work it out for when the cosmic microwave background was released, right? Light travels at the same speed, the universe is 380,000 years old, which means the horizon was about 3.6 billion trillion meters. or
All right,
380,000
there
light
you go.
years.
Causal.
So when the cosmic microwave background was emitted, only the parts of the universe that were within 380,000 light years of each other were able to influence each other or transfer information. Like, for example, in a heat transfer to evenly distribute the energy around so the universe is all the same temperature. And yet, when we look at the cosmic microwave background coming from all directions, it's roughly the same temperature with the same spectrum of light in all
could be playing
locations.
on this,
despite the fact that when the cosmic microwave background was emitted, those different parts of the universe were beyond each other's horizon. They will never have come into what's known as causal contact with each other. This is what the horizon problem is. And essentially, it means the cosmic microwave background shouldn't be as smooth as it is. Yeah, all right, there are these tiny fractional changes in the temperature, which are, shown in this classic diagram of its detection, with the colder spots being the places that gas first cooled enough to become dense enough to form stars and galaxies. But given the horizon problem, the cosmic microwave background should look vastly different, like with huge temperature fluctuations from one part of the universe to another, leading to a much more clumpy universe where matter is less evenly distributed. This was first pointed out in 1956 by Rindler, back when the existence of the cosmic microwave background had been predicted but not yet observed. So since when we observe the universe, it is much more homogeneous with matter spread evenly and also isotropic, i.e. looking the same in all directions, then we had to be missing something in our best model of the universe. So what are some ways that we can solve this problem? What can we add to our best model of the universe? Well, the most widely accepted way is through an idea called inflation, which was first proposed by Guth in 1981. And inflation is the idea that very early in the universe's life, the universe expanded at an exponential rate, increasing its size by a factor of 100 trillion trillion in just a trillion trillion trillionth of a second. What it means is that inflation takes the parts of the universe that were inside the horizon and expands space so rapidly that they're now outside of the horizon. Parts that used to be in causal contact with each other and could influence each other and reach that temperature equilibrium then become bigger than the entire observable universe at later times. Meaning that in every direction you look, the universe will look the same, and the cosmic microwave background will have the same average temperature. And it's not just the horizon problem that cosmic inflation solves, it also explains why the geometry of the universe is flat, and it explains why there's no giant magnetic monopoles hanging around space. So it's had a lot of successes, and yet people still don't like it because it is a little bit wishy-washy. Change one of the parameters a tiny amount and you can get any behavior you want out of inflation and therefore any look to the universe. So some people argue because of that it doesn't really meet the standards of a proper scientific theory, but then others argue that by measuring properties of the universe more precisely we can then narrow down what the properties of inflation should be, and we should be able to fine tune it like that. But the biggest issue to me though as an observer rather than a theorist is that inflation isn't really testable with observations, at least not with our current telescopes and their limitations. So obviously other ideas have cropped up over the years. One of the more popular ideas is that of a cyclical universe, where you're going through these endless cycles of Big Bang expansion, which then at some point turns back around into a big crunch contraction. After a couple of cycles, this acts just like inflation because you bring all the areas of the universe into causal contact during the crunch, which means that during the next Big Bang expansion period, you've then got the entire universe in thermal equilibrium, leading to this homogeneous universe where you have this even distribution of temperature seen in the cosmic microwave background. Wouldn't get excited though because these cycles are expected to last trillions of years, so it's not like we're about to see... I wouldn't get excited though because these cycles are expected to last trillions of years, so it's not like we're about to see and find some evidence that the universe's expansion rate is slowing down and we're going into a big crunch. Plus, also, the cyclical model of the universe doesn't explain as many of the things as inflation does. It really struggles to explain away this, giant magnetic monopole problem as well. And then, of course, you've got these models.
And that is an interesting point, too, because it also was a problem, and I'll do a video on this at some point, that when you consider sound, sound does not travel through the vacuum of space. Right? Sound travels in waves and it requires a medium through which to travel. Now, when you apply that same thing to light, how is it that light, what is the property of light that it can come through what is essentially a vacuum, the vacuum of space, and yet those waves, and it's also bits, are able to travel through a vacuum. What medium are they traveling through, on, in, however you want to word it, that differentiates it from sound? But why does it? Why is it allowed to come through?
That try to vary the speed of light. You know, this speed limit of the universe, which ultimately sets the size of the horizon. So in these ideas, what people are saying is that in the early universe, light can travel much faster. So the horizon problem essentially disappears because all the universe can be in causal contact with each other. But these sort of varying the speed of light ideas really struggle the most with sort of explaining the horizon problem, because as soon as you start tweaking the speed of light, you've got a long line of dominoes that you've knocked over, you know, like bits of physics that all start breaking that have, you know, long been supported by observational evidence. So where does that leave us? Well, it leaves us with a horizon problem that for now is best explained by introducing inflation into our best model of the universe. But our best model of the universe is facing pressure from other areas of astrophysics that I've talked a lot about on this channel before, which could lead to some scientific explorations of new physics, you know, in the next decade or so. And who knows what might pop out of those scientific explorations? You know, it might be a new solution to this long-standing horizon problem. And if that's the case, all I hope is that whatever solution people come up with, it is actually testable with our observations of the universe. Get off my face hair. Oh, you know when like one hair just like gets absolutely in the itchiest spot. Big Bang expansion, which then at some point turns around into a big crunch. What's the opposite of expansion? De-expansion? No. De-expansion. Contraction.
This happened. I know the feeling of this, because we don't. When you're doing these videos, and you're constantly coming up with new ideas, and you want to make them relatable and articulate and such, it's amazing what you discover about yourself on camera. But all that aside, this stuff is absolutely like fascinating, and I love the perspective that things are going to change. They might change, even the laws of physics. And once you start tweaking the speed of light, and that might happen. That, I mean, we take things as rock solid, intransigent. It just will not change. And we cannot let it change because all these other dominoes will fall and it'll be chaotic. But that's what happens. If you want, I ran into the dean of the Rutgers math department a couple of years ago. I didn't know he was the dean. It was just a guy outside smoking a cigarette. And I just struck up a conversation with him. And when he said he was the dean of the math department, I asked him right away. I said, "What's the latest crisis in math?" Right away. He said, "Quantum mechanics is not lining up with probability theory." And that's a great question to ask anybody, by the way. Anybody in their field, what is your crisis, especially in academia? What is the latest crisis in your field? Because there's always a crisis. It's just human endeavors lead to crises. It's like we come up with our favorite theories. They agree with observation. They agree with our logic. They might agree with our math, and then they don't. At some point, because people are always looking out to not only make a name for themselves, and that's not pejorative, but people are working on different theories, and at some point something's not lining up. Like with Galileo, looking up at the rotation of the sun, the stars, the moon, all this to the planets, and it's like, I don't think everything goes around Earth. We go around the sun, and they should can him for that, basically. And I think the Catholic Church in the last 10 or 15 years recently pardoned him. Like, if that matters to him, but they cleaned his name from being a heretic. But theories change, ideas change. Even our most valued theories, such as the speed of light, it might change. And if it does, the dominoes fall, we rearrange them, and hopefully a better understanding of what we've been observing comes shining through, literally, from the speed of light. So, all right, this is wonderful. I like her. She's just fun. She's affable, amiable, knows her stuff. She presents things to the public in a certain way that can be understandable. Sometimes you have to rewind the the thing and then watch again. But hey, it's worth it. All right, guys, hope you enjoyed that. Have a great day, and I'll see you on another video. Hey, folks, if you want to take the personality test that I created for my life coaching practice, which is based on the book that I wrote, put your phone up, turn it on camera, and focus on this, and it'll take you to it. And it'll take you about 20 minutes to complete the test. It's free, and you'll get some information on your personality. It's quite detailed, quite revealing. It's kind of fun as well. And I'll be leaving this QR code up on the wall behind me for my regular videos. So I hope you take it, and I hope you enjoy it.